Thank you. Thank you very much. Thank to the organizers for inviting me here. I'm very happy to be here in spite of 24 hours of travel and the horrendous weather we had over lunch, which probably my voice will... I didn't coin the, nom is too generous. I didn't coin the term biolinguistics. I mean, I thought that was what it was. I mean, they had, a seminar at MIT, Salvador Luria, Nobel Prize for Medicine, and Chomsky. They had a seminar with biologists and linguists. That was biolinguistics. So I think that's what it was. Now, the most important term in this title is this, steps. It's just the beginning of something. I'm going to tell you about ongoing research. And it's something that we think, David Medeiros, Juan Uriagereka, before he came at SAR in this university and is mostly doing, unfortunately, administrative work, we think we have opened a Pandora's box. New and new things come, once you have this approach, I will highlight very briefly to you. More and more things come up, and I have, every other, not really every other day, but every other week, David Medeiros comes to see me. He has found another application of this thing. And we have to stop him because he now has to finish his dissertation. He already defended. He has to finish and deposit this dissertation. I say, stop with this. Write down all you have done so far, and then you have a lifetime to continue. So we really think it's very productive. Now, this is a quote by the great Richard Feynman. Cedric Burks is very familiar with this. He said, when I was in high school, my physics teacher, whose name was Mr. Bader, called me down one day after physics class and said, you look bored. I want to tell you something interesting. Then he told me something that I found absolutely fascinating and have since then always found fascinating, the principle of least action. Really fascinating. So we are threading in the wake of the principle of least action ourselves. And again, Feynman, in his lectures on physics, something as a physicist I studied, Physics 101, some zillions of years ago, he says, now, in the further development of science, we want more than just a formula. First, we have an observation. Then we have numbers that we measure. Then we have a law, which summarizes all the numbers. But the real glory of science is that we can find a way of thinking such that the law is evident. This is really beautifully said. My emphasis there. So this is the plan. First part, what is language? That you want to find the physics of. I don't have to tell you what language. I'll go very quickly on this. Second part, what is the physics we want to find for language? And then trying to put all this together. And then, time permitting, some lessons and conclusions. These are the third factors have been evoked here already today. Third factors in language design in Noam Chomsky's characterization, facts about language which are neither encoded in the particulars of our genome, nor learned from the environment, but determined by domain general principles beyond the organism. So something coming from physics and mathematics and criteria of optimal computation. I like this sentence because it was on the front page of the New York Times in 2009, and it happened to be published just when my friend and colleague Heidi Harley was putting together, as she has in the meantime, a software to create syntactic trees. So I say, okay, you have this program to generate syntactic trees. Why don't you draw the syntactic tree of this sentence? Top federal regulators say they were taken aback when they learned that the California congresswoman who had helped set up a meeting with bankers last year had family financial ties to a bank whose chief executive asked them for up to $50 million in special bailout funds. This is English, front page of the New York Times. Now, I think in the next days you will hear a lot about language evolution, and my suggestion, don't settle for anything less than this. Okay? Because one thing try to explain, and some probably will, try to explain, John kicked the ball. Maybe you can explain the origin of John kicked the ball. We want to explain the origin of this. This is a syntactic tree with 32 levels of embedding. You will not be surprised, and it could continue. You don't have to stop at 32. Because one can say, you will never going to believe me, but the New York Times says the top federal regulators, blah, 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 and you can continue and continue. We don't have to stop at 32 levels, so it's indefinite. Okay, it's 4 full pages in PDF, and why do we have such a structure? This is just the top of the syntactic tree. I don't have to remind you that there is a lot of repetition, of the same fundamental components, and then you have again and again and again and again the same structure, which is the X-bar structure. So what we want is the following. We want the syntactic dependency to remain as local as possible, and do not multiply in kind, and then we want the overall number of such dependencies to be minimized. But the syntactic structure must allow for further expansion, theoretically indefinitely so, under the constraints of preserving the structure itself. What we have here, as you will see, I hope in a moment, I'll show you self-similarity. So, the first basic strategy, all well known to all of you, is merge. You have elements that within a phrase belong together, and the most basic way of doing this is to form a set. The minimal set is 2 members only, so we form a set of 2. And then we continue doing this because we have phrases in a sentence also belong together. The most basic way of doing this is form another set, the minimal set, 2 members only. And then we have headedness or endocentricity. We do not want to multiply entities, especially kinds of entities, beyond necessity. So we treat the whole as being of the same nature, the same kind of entity as one of its members, and we do it again and again and again until the sentence is completed. And the strategy number 3 is locality. Not all members are equal. There are hierarchies. Familiar with C command, it doesn't much here matter how you exactly define C command. In what we are going to say, it can be the Unas Portish definition in terms of maximal thing, or it can be the previous definition. Make it as small as local as possible and continue doing this until the sentence is completed. And then you apply the same operation to the output of the previous one and keep doing this until the sentence is completed. What is the perfect solution to all this? Well, you minimize the number of local dependencies, you minimize the number of relations of C command, and no matter how deep is the structure, but you have to allow it to grow as much as it needs to. And this structure is, surprise, surprise, none other than the X-bar structure. This structure, well known to you. Okay. Now, an interesting aspect of this structure is that this can be something exactly like the four. This as a whole can be this, and then as a whole can be this. So you have something that you see highlighted here is the same structure repeated, and then you have first level of recursion, second level, third level, fourth level of recursion, and it can continue. Okay. So the winner is a minimax solution, as you have in physics, as you have in biology, as you have in neurobiology, I'll show you, and as you have in game theory. Don't have time to go into that, but much beyond. So the physics of minimax solutions, you have 2 conflicting forces, and you have to be composed, and you have a serial buildup of patterns, and what you have is the universe of relations that are the Fibonacci patterns. I will show you, for those who are not very familiar with that in a moment, various aspects of this nucleus of mathematical relations. And you find them in organic structures, in plants, animals, in language, and even in galaxies. So this is the Fibonacci series. Each member is the sum of the previous 2. And then very rapidly, the ratio between 2 successive numbers converges to the golden section, approximately. It's a number that it continues to infinity, approximately 1.618. Here you have the bones of foot, but you find it all over the place. You have a Fibonacci sequence here. Here, this is the molecule of DNA. You have a larger groove and a smaller groove. The ratio between the size of the larger groove and the smaller grooves is the golden section. This is how you build the Fibonacci spiral via the Fibonacci series, and these are a few, just a few, of all the instances of the Fibonacci arrangements you find in nature. And what you find is not only Fibonacci structure, Fibonacci, but you find that the number, going in this direction, clockwise or counterclockwise, you have two Fibonacci numbers, 21 and 34, and so on and so on and so forth. The Fibonacci spirals all over the place. Now, this is a very fine article by two French physicists of a few years back, published in the Physical Review Letters, where you have the complete, total, all the equations and everything. So what you have here, you have drops of ferrofluid that fall onto a silica, dense medium, and they are attracted towards the circumference here, toward the side, and they repel each other. And after you let a certain number of drops fall, you see these very nice Fibonacci structures appearing. This is a perfectly inorganic, perfectly well-designed system. In fact, they published these as phyllotaxis, as a physical self-organizing growth process. You can find this on the internet in real time. It takes 5 or 6 minutes. I don't have the time to show you the movie. You see them being formed one after the other and after the other as the drops fall. Okay. Now, what you have here is that initially two successive drops depart one from the other at 180 degrees, but as you keep adding drops, very rapidly they converge onto the golden angle, 137.5. Very rapidly that happens. And here you have the Douadi and Couder pattern, and here you have one of the many manifestations of this pattern in biology. Many other examples. These are just a few. If you Google Fibonacci structures in biology, you find plenty. Asymmetry in the mammalian bronchial structure, consistent with the process of morphogenetic self-similarity described by Fibonacci scaling. The distribution of the frequency of bandwidths in EEG. I don't know why it's doing this. According to the Fibonacci-related golden mean, and they explain what you find in this paper of 2008, that you have a way to pack as many minimal interfering frequency bands as possible into the available frequency space. Now, Stuart Hameroff is a neuroscientist. He's the head of anesthesiology at the University of Arizona, and he came, Chomsky came in February. He gave a talk, and Stuart Hameroff was there, and he heard Chomsky say that syntax is basically a snowflake. He was absolutely delighted that he heard that the syntax is a snowflake, because he said we have the snowflakes, not syntax. They have snowflakes in the fundamental constitution of inside the neurons. And 3 days ago, this paper was published. You can find it on PLS Computational Biology. So here you have a complex, a molecular, indeed, it's a snowflake. It looks like a snowflake. So this is a calcium calmodulin-independent protein kinase 2. And what you have here, it is a structure that is activated by the calcium influx, and then it's phosphorylated. These are the phosphorylated sites. So it is a structure that has 6 bits of information. And then when it is being phosphorylated, this you see from the front, this you see from the side. When it is phosphorylated, this is from the side. You have these little legs. You have these 6 legs that protrude down. And it is a very, very important, very frequent molecule. You find it all over the place in biology, in many signaling cascades, in calcium homeostasis, reuptake of cardiomyocytes. It's all over the place, positive T-cell selection, and so on and so forth. So these 6 legs match precisely the hexagonal lattice of microtubules. Microtubules are part of the skeleton of every cell. They are all over the place in every cell, but in neurons they have a particular lattice that they form, and the snowflake that you have seen, the calmodulin, adheres very precisely to the microtubules, and then you have long-term potentiation. You have, at the very least, memory. You can justify how memory can be formed and can be stabilized for so long, sometime during a whole lifetime, at a deeper level. Moreover, the grid cells in the entorhinal cortex, very, very important formation, interfering and communicating with the hippocampus, very, very important for the formation of memories and the formation of spatial maps, are separated, guess by what? By the golden mean, 1.618. So you have this molecule that you have seen a moment ago, which adheres, as is seen from the front, onto microtubules that are this hexagonal structure that can, in some cases, be many centimeters long. They can be fraction of a centimeter or many centimeters long. And what they do is they facilitate, these are tubulins, dimers of tubulins. The one that you see in dark, they are in an activated state, and there is a propagation of this activated state. These are cellular automata, literally cellular automata, and they develop in their paper the theory. And lo and behold, what you find is that the propagation of information along the microtubules is the Fibonacci pathways, 853 from left. So you find them in the brain, you find these Fibonacci structures all over the place. Now, it has been shown a few years ago that if the dimers in these cytoskeletal microtubules forming a Fibonacci spiral, this gives the optimal way of transmitting and storing information. You couldn't do better than that. Okay? So they are cellular automata transmitting information. This is the physics we want now to find. This is, without going into the detail, this say that what you have is a fractal. You have something that repeats itself from times of the order of 10 seconds all the way down to terahertz. Okay? So you have scale-free dynamics from very, very small structure all the way up to whole neuron networks. It's very interesting. You have a fractal, you have something that is conserved across very, very interesting orders of magnitude. And here you have, this is, traditionally, Leonardo da Pisa, Filius Bonacci, known as Fibonacci, he had this curious idea of calculating how fast does a colony of rabbits reproduce. And he has this thing. So you have the twos are an adult reproductive pair, the one are the juvenile sterile pair. But let's forget about rabbits. This is the structure that he has discovered at the time. And now, instead of rabbits, you have X bar, which is 2, and then you have X prime, the first projection, that is 1, and you have the Fibonacci series. So basically what you have in the Fibonacci string, instead of having the sum, the general formula is that each member is the sum of the previous two. Here what you have that each member is the concatenation of the previous two. And so you go to the Fibonacci string. Why is this Fibonacci string so interesting? This is the recipe, how you get it. If you see this, you substitute with 1. If you see it, you have like 1, 0, and so on and so on and so on. So you have the rule of continuation of the series is contained in the series itself. And you can regenerate the whole series from any part of it. So it is a fractal. So the golden tree is self-similar. Its linearization is also self-similar. So you have the property of self-similarity at many scales. Okay? Now, I hope you will hear, because I'm going to show you. So it is the simplest, most elegant fractal you can possibly have, because its fractal dimension is logarithm between base 2, this is what you want, and base 2, of phi, of the golden number. So the sequence encodes its very own procedure, and I hope you will hear now what an acoustic Fibonacci series sounds like. Now, this is extremely interesting because Doug Sadie at the University of Reading, already a couple of years ago, has tested adults with this sequence, the sequence you just heard, which is a Fibonacci sequence, with other 5 superficially, only superficially sounding like the sequence, but not being a Fibonacci sequence. And he says that now he's trying with children, he's trying electroencephalography and brain imaging. I don't have the data to report to you. But the data that I have, that he has already published, are these. So this is ease of memorization and ease of generalization. The gray bars are the Fibonacci. And these others in black are variants that superficially look like the Fibonacci, but are not. So they are better remembered, better generalized, and better processed. Now, it's very important. The Fibonacci sequence, as you see, has a lot of internal, sort of optimal internal structure. But it has no statistical regularity. I mean, if you have just heard 1, you don't know what is going to be the next 0 or 1. If you locally, just know, I heard 1, what I'm going to hear next is 50-50. So it has no local statistical regularity. So the facilitation that we have in memorizing and in extrapolating a Fibonacci series is not a statistical regularity. It's something much deeper and more interesting than just a statistical learning or statistical regularity. Bring this in mind. In the following days, you will hear a lot about statistics, but bring in mind this, please. So these are found everywhere. Syllables, this is already goes back to Rhyme and Reason. Juan Uriagereka several years ago. Extension with Billy Sardi to prosody. Interesting have to do with words, but what for time constraints I will only go into syntactic structures. It goes also into the alternation between phases and non-phases. So this is the platoon of the crazy guys, of which I am one, I'm proud to be, who study Fibonacci structures in syntax. And as I said, it's just the beginning of something we think is really, really very interesting. So here you have the syntactic tree, and at all levels of the syntactic tree you have Fibonacci numbers. So this is the maximal projection, this is the first projection, this is the base, and you can continue and continue and continue. And what Dave Medeiros has shown, very interesting, is that an optimal tree. You couldn't do better than this. Also, he has this interesting theory that movement, syntactic movement, or copy deletion, if you prefer, is a tree balancing operation, is the best that you can possibly do. Also, if you keep adding terminals to a sentence in a syntactically legitimate way, you force a higher level of embedding if and only if you reach the next Fibonacci number. Okay? So here you have this structure, then you get the next Fibonacci number, and you have a higher level of embedding, and it can continue and continue and continue. Interesting property. Now, what are the interesting properties of what he has called the golden phrase, which is X bar? Well, there are 4 considerations. One consideration is that the simplest kind of syntactic binary multifractal. You cannot do better than that. It's the minimal semantic generator, the first shape to unlock the full set of predicate argument meanings. And then you have the specifier head complement order, yield string related to the golden string, infinite Fibonacci word. It has the lowest ambiguity among binary generators of binary. And finally, the mapping of hierarchy to linear order and its converse are straightforward, which is very important because we parse in real time in a linear segment, but the hierarchy is what it is. So we go from the hierarchy to a linear sequence, and those who are listening to us go from the linear sequence to the hierarchy. Well, this mapping is absolutely perfect. You couldn't do better than that. It's really an optimal structure. Okay. Now, it seems to have to do with double articulation that has been evoked here earlier. So you have this potential of development on both sides, on 2 asymmetric sides. So you have something like barbarian destruction of Rome, and then you have the barbarian destroyed Rome, and then you have the phrasal off branches on both sides. It can be expanded. The ravening halls of barbarian destroyed, the gleaming city of Rome on the hill, and so on and so forth. So this arrangement has all these very, very nice properties. Now, C command, you are all familiar with C command, so you see even very, very simple structures like this, very simple trees, they have different numbers of relations of C command. And the hypothesis is that you want to minimize the number of C command relations. And you do this by moving things around so as to minimize the number of C command relations. You really want to have the minimum. And so you have a bushy structure like this is better than this because it minimizes the number of C command relations. And here you have how the number of C command relations grow as you grow more and more and more terminals. So you see that this is the spine. If you continue growing as a spine, they grow very fast. If you have the bush, it grows a lot less fast. So, it's much better to have this than to have this. And here you have, for the same radius, so to speak, the same number, it starts sort of low, and this is the total of possibilities, which already, for radius 11, knots, you have 20,000, but then you continue, and here you have 27 million. And the number of solutions, of these solutions, is only a fraction, a tiny, tiny fraction of all the possibilities. So it makes a lot of sense that you have one of these very few possibilities instead of contemplating this monstrous number of what is only theoretically conceivable. Now, this is the fundamental movement condition that you have here. So here you have these two syntactic structures, and here you have this, the movement, this has moved here. What is the criterion? The criterion is basically that the number of nodes here multiplied by the distance by which you move must be greater than the number of what is left here. So here you have a couple of examples. You count the number of nodes here, and you have that this is okay. And also you have that if this is what happens, this is kind of movement you have, also you have that this is okay. So intuitively, you multiply the number of nodes in the moved structure by the overall distance moved, and it must be greater than the number of nodes in the unmoved tree, because then you make the calculation of all the C command relation, and this is exactly what you want. So movement is justified if and only if it balances the overall tree. The physics of language must have to do with balancing, must have to do with equilibrium. Okay, this is what we know from physics. So a small subtree moves far enough, or a larger tree moves only locally, always compensating for what is not moved. This is a very fine application that Dave Medeiros has developed of this idea that may sound too abstract to a number of us. And you have Guglielmo Cinque's recent analysis of the possible orders in different languages of demonstrative, numeral, adjective, and noun. So in English, these four blind mice is perfect. Mice, these four blind is horrendous. Mice blind for this is horrendous. But in other languages, you have other orders. And this goes back to Greenberg, 1963, when he says where all of the items, demonstrative, numeral, and descriptive adjective precede the noun, they are always found in that order. If they follow, the order is either the same or its exact opposite. There was something right about this, but not quite right. And this is Cinque's summary of what you have in all languages that he has examined. He has examined many languages and dialects. So in white, you have the attested orders, and in gray, you have the unattested orders. So it's really different from what Greenberg had, okay? Because Greenberg's generalization would have excluded this and would have allowed this. So this is the best that we have, and the explanation is exactly what Medeiros has supposed. Movement of the DP affects the NP, or an XP properly containing NP, no head or remnant movement, and so you have all the different possibilities under these following assumptions. You have the assumption of universality, that DP orders of every language represent transformation of a single common base structure. Coherence, they correspond to coherent subtrees, each one of them, that cannot be broken apart further by movement. Monotonicity, all movement within the DP must satisfy the condition you have seen, the fundamental movement condition. And then continuity, every monotonic derivation corresponds to an attested order, and that is indeed the case. What now Dave Medeiros is doing is extending this kind of analysis also to verbs, to the organization of verbs. So you have modals, auxiliaries, verb, and particles, and it seems to work for those two. The data are not solid enough for me to project them to you. So these are just two examples. You have this order, and this is okay, and you have this order which is not okay, and then you compute, what you get here, you have an advantage, because you go from 124 C-command relation to 104, you diminish them, so it's great. Here you couldn't do this because you would be going from 114 C-command relation to 124. That is bad, that you don't want, so it is an order that is not attested. Here, by going into the detail, this is Dave Medeiros has been calculating all the possibilities. So what you have in red here are movements that are forbidden. What you have in these black arrows, movements that are allowed. It is sort of a complete classification. Drives one crazy. It didn't drive him crazy. He has done this, and it is a summary of all movements that are allowed and movements that are not allowed. So what he has shown is that assuming that movement is for reducing the number of C-command relation, what you have is a single principle that accounts for the typology, at least, of DP orders, and we think that this is really in harmony with what we want in a syntactic inquiry, in a minimalist syntactic inquiry, because you are drawing accurate maps of syntactic structure and describing the constraint of movement within and across languages on the basis of a very, very simple physical, computationally optimal constraint. So all these strands are united in a single study. Patterns of movement, diagnose structure, and a structure determines possible movements. This looks to be very, very nice. Now, finally, notice the following. I said the physics of language. The physics of language, which is that you don't have, across all the things you have seen, all these different manifestations of Fibonacci structures, you keep finding them because the laws of nature apply. You do not keep finding them. A bit unlike what Stuart Hameroff was suggesting. You don't find them because there is a percolation of them all the way up, all the way down, or inheritance of one from the other. A laws of form physical explanation makes no claim of percolation, makes no claim that things filter down. It's a different kind of application. It's a different kind of explanation. It is reoccurring because the same principles apply again and again. And these principles are very simple, very elegant, very essential, parts of optimal computation, from physics to biology to language. So these are laws of minimalization that apply all the way up. And Feynman was right. This is interesting. Minimality principles are really interesting. And if one was bored by, whatever physics they were teaching him, if one was bored by, older ways of teaching language, perhaps one was right to be bored. Now you look at these things, and then this is, I think, fascinating, and it is the beginning of a kind of analysis that, for all its incompleteness and being still very tentative, I think points the way to something that we like, something that we think is a productive way of explaining things, not just positing them, but explaining as best we can on the basis of very fundamental physical principles. Thank you.
Okay, so we have 24 minutes. We move on to the questions and answers session. The procedures is totally the same in the preceding sessions. So,
It's fine.
I have a comment and a question about this very nice talk. Both of them are puzzles. The question first is, you mentioned a couple of times what kind of physics we want, and then you mentioned the physics of Fibonacci. But I thought, and correct me if I'm wrong, that there is no physics of Fibonacci. That is, people don't know what the laws are that give rise to the structure. That is, it's true that the structure has been identified in many contexts, physical context, biological context, and so on and so forth. But they are not sure which are the mechanistic laws that give rise to that representation of structure that is done over and over.
Can I immediately react on that?
Yeah.
You know, Douadi and Couder have the full theory. They have the equation, they have everything, okay? And this is an instance of having two opposing forces and combining two opposing forces. They suggest that in botany, you know, in the organization, it will have exactly the same thing. The title of their article is, you know, they are not so much interested in these drops, they're interested in explaining biological features, so you have the whole theory there.
Well, perhaps you know better than me, but I thought that at least the experts were not convinced by the explanation because, for example, it depended on the rate of drops, and so many experts didn't buy that particular explanation. That's why, for example, you have colleagues in Arizona still trying to find the laws behind Fibonacci. Anyway, that was a comment. The puzzle is about the work by Medeiros that you have pointed out, and the puzzle is the following. If I understood correctly when you showed the slides, that the bush, that is the bushy trees that minimize the sequence relations, is preferred over the spine.
After the spine has grown a certain length, yeah.
That's exactly the puzzle. That is, it seems like we have a system where the spine is actually favored up to a point. Specifically in the context of the DP, you basically construct the spine introducing all the functional projections that you need, and only then do you react to then minimize C-command relations. And the question is, isn't this a puzzle? That is, why doesn't syntax fix the spine as it grows? That is, why does it wait until you have introduced the full functional sequence to then fix the problem? This is something that seems to go against a principle of fine computation that Chomsky often alludes to, namely cyclicity, where you fix things as you go, basically. And this seems to be one where you fix things once you're done.
Well, what is the case? Sorry, I'm losing my voice. You start putting together by multiple, structure building. You start putting together, these things in that way. Then, when local search and the number of local C-command relations is growing beyond a certain limit, then you have the advantage of moving. You have the advantage of reorganizing the tree in that way. When you have very few of those nodes, then you have those solutions, the difference between the solution is really too small. When you keep doing that, then the movement and the reorganization really becomes significant. That seems to be the case. Yeah.
So, I have a bit of a problem with what do you actually explain with the finding of Fibonacci series in language. I agree with the elegance of Feynman about the least action principle in physics. So in physics, the action is what is optimized for. But in biology, as Cedric noted earlier, what is optimized for in physics is typically not simplicity and elegance, it's robustness rather. And it's interesting that Fibonacci series pop up all over the place. But what explanatory powers do they have? and what causal powers do they have? Is it not rather that Fibonacci series pop up in those places where whatever is optimized for happens to give that pattern? If you put the pattern before, you put the causal cart before the horse, or what powers do you actually give the Fibonacci patterns?
Okay, so the Fibonacci's patterns are an emerging pattern. Okay, what you have, the forces are, for instance, in the growth in the phyllotaxis. You have the tendency to grow on the one hand, and the other, whatever already is there to avoid, the contact or overlap with what is there already. And these are the forces. And the best way to put together these two forces in the minimax solution is the pattern that we see there. So what is the puzzle? I mean, what is that you're perplexed about?
Because one could get the impression in your speech that you claim more than that for Fibonacci.
More in which sense?
That there is something, well, you seem to put very great, how to express it, you seem to make a big thing of finding Fibonacci in language, as if that in itself explained anything. Or is it rather that you argue that language, the Fibonacci series in language is emerging from language being optimized for minimal wiring, as we express it?
Well,
and if so, why is language optimized for minimal wiring and not for something else?
it is optimized for all the things you have seen. It's the optimal solution of having this structure between the linear and the hierarchical. In the hierarchical structure, it's minimize the number of hierarchical you have to have, and we have hierarchical dependency. The idea is to minimize the number of hierarchical dependency. You do all that, and this is what you obtain. So it is an explanation, just like it is an explanation for the drops of ferrofluid or the biological structure, that you have these interacting principles, and what you see there is what emerges. It's the same kind of explanation.
You just said that Fibonacci sequences emerge from physical dynamical interactions. What are those physical dynamical interactions among nodes in the syntactic tree?
Well,
because all the other instances were actually physical, biological in some way, but what about nodes in the syntactic tree? What's physical about them that forces them to interact in a certain way?
Well, you have binary branching, multiple repeated recursive binary branching. You want to do that, and you want to do that in the best possible way. And then you have to have this linearization on the one hand, and then from the linearization going back to the structure. And all these are best satisfied by this structure. We show that this structure is the one that satisfies all these requirements best.
But I understand that if it's cells that are interacting, parts of plants and how they pack, because there's physical interaction between them. But I don't see any physical interaction between syntactic nodes, and they're just an abstraction. They're one particular way to represent what's going on.
Okay. Look, let me answer in what may sound to you a very curious way. I hope it's not, and I'll explain why I'm answering the way I'm answering. I'm sure you're familiar with Pauli's exclusion principle. It says that no two electrons in an atom can have all their quantum numbers alike. This is physics. It is a physical principle. It doesn't mention forces. It doesn't mention fields. It mentions quantum numbers. No two electrons can have all the same quantum numbers alike. And it explains the periodic table. So physics, you have to interpret physics not just, just like contacts between things and things that pull or pull. Pauli's principle is a purely formal physical principle. So there are such things as formal physical principles, and we have some here.
Uriagereka has difficulty with that.
You don't think that Pauli's principle is physics?
No, I don't think that syntactic nodes have the emergent properties necessary. And my problem is that that's one way of representing those things that a lot of us have adopted. But it's just a convenient one, particularly because it has visual properties that are simple to grasp immediately. But I could represent exactly the same relationships with a set of rules or other sorts of representations.
Well, if we are remotely right, it's not just a convenient graphical way. It's really what the phenomenon is. If we are remotely right, we may be wrong.
I have these related questions about the Fibonacci numbers in phrase structure. Well, I don't know for sure, but is it simply that whether you detect Fibonacci numbers in phrase structure totally depends on how you analyze phrase structure? For example, how many functional carriers do you have, or how do you analyze lexical items and so on? So borrowing Jack and Rose phrase, your theory of the Fibonacci totally depends on your theory of phrase structure. Is that so?
No, I wouldn't say that.
Really?
Look, it depends on the following. You have to put together things. And the minimum number of things you have to put together is 2. So you have to have this binary structure. Then you have recursion, because we know we have recursion. So you have recursion, binary structure. And given recursion, given binary structure, then this is the best way to do that.
So whichever theory of phrase structure you may adopt, the result is the same. That's what you're going. It's always a Fibonacci.
Well, let me put it this way. We knew already as a fact that you have this structure, the X-bar structure, that it is, this recursive structure in which it is itself a part of the same structure and so on and so forth. So far, we knew that as a fact. That is a fact, an interesting fact. It took a long to come to that. It's an interesting fact. Now, I think we are suggesting an explanation why you have that structure and not other structures. And all kinds of different trees, binary trees have been examined, and they are all found to be not as good as this one. So this seems to be the best of all possible binary trees, of which you can invent quite a number. This is the best. So we think we have an explanation for something we knew already, but we knew it without being able to explain it.
But X-bar scheme is now just an epiphenomenon of the binary branch. So you can't just derive the binary branching property from X-bar scheme.
Well,
It's just because you have binary branch.
Well, we know we have binary because that is the minimum number. Okay.
Yeah.
Okay. So, well, there are a number. Richie Kane, when Richie Kane explained and justified the binary branching, had a number of very interesting data to back it up. So, it was binary because it was, the generalization, interesting generalization from a number of linguistic facts. Now, in minimalism, you have a different approach. You have to put things together because a sentence is not a list of words, obviously. You have to put things together. What is the simplest way of putting them together is to form a set that is of the same character as one of them, and you keep doing this. So the logic behind that, it is the simplest possible structure, and so that is already something. That is the simplest possible structure. You put 2 of them together. You can't put 1. You can't put more than 2 because 2 is the minimum number. And then given that you keep doing this, and you keep doing this, and you keep doing this, then I think this shows that that is the best way to do it.
Oh, don't misunderstand me. I couldn't agree more with you, but I'm asking this question just for clarification, because other researchers have different scenarios, different theories about phrase structure. For example, take Ray Jackendorf. He does not adopt much, but his theory is dependent on the operation unification. And the resulting phrase structure is completely different from what we minimalists generally assume.
Too bad for him.
Oh, yeah. That's the point.
I phenomena, how, in what sense are they natural law? In what sense they reduce complexity? So this approach is perhaps a global approach to
Yes.
reduction of complexity, because you have to compare all the possible
Yes.
outcomes and then select the part
Yes.
comply with the
Yes.
natural law. So
Yes, well, yeah. So, I mean, just to insist on the following, I didn't have the slide, it would be been too long and too complicated, but you consider all other conceivable alternatives, and then you see how these other conceivable alternatives fare, and they fare worse than this one. So, this is the best. So, as you have the minimum action and minimum path in physics, we think that when you have the best solution, the minimal solution, this is what nature usually adopts.
yes. And then the question arises, what remains
Oh,
in such a way that we recognize an object as being natural language and not a cauliflower, right?
sure. Then we enter your domain. We enter, the lexicon, the organization of the lexicon, and all the trait and morphology and all that. And when you have a structure like this that takes in those things, then you have language.
Any other questions or comments?
Sorry, I hate to insist. I will not defend Jackanoff, but it's going to be a comment related to, I think, what Dennis and Koji were trying to get at. If you look at the results, it crucially depends on the correctness of the X-bar schema in some fashion. But as Chomsky has pointed out, the X-bar schema stipulates at least one thing in addition to the binarity of merge and recursion. Namely, it's known that the X-bar schema depends on there being only one specified position before the maximal projection. Okay? But if you remove that stipulation and you allow for multiple specifiers, then it's very hard to fall back on the Fibonacci number. That is, you need one extra condition that you didn't mention, and that one doesn't seem to follow from binarity of merge or recursion.
Okay. Now, multiple specs is a delicate and complicated thing, okay? What David Medeiros has, I'd ask him to send, he's developing this. When you have multiple specs, it seems that you can only have, as we know, in certain position with certain architecture, okay? Multiple specs. And then you have these additional constraints, this additional of having not just one spec, but having multiple them. And this doesn't compromise the theory. In fact, it expands it. He has something that is under, he's developing as we speak to explain if, assuming that you have multiple specs, and in some languages seems to be the case, Japanese, you have this, multiple subjects and all that, that this approach tells you what is the best way to have them.
So your Fibonacci syntax says something about right branching structure. What about, say, left branching structure, like, say, John's mother's car? Left branching.
Well,
And a lot of, say, possibilistic modifications in that structure, right?
yeah, well,
So in that case, your theory allows what movement?
the direction of movement is not specified here. The condition is that you have a number of nodes, and then you have the distance which is moved. Right or left is in this theory cannot tell you about right or left. It is not. It can be one or the other.
Yeah, but in that case, sort of say left branch condition works. So that's not the case in right branching structure.
No, it is the case in both. What this theory doesn't tell you is whether, you should be doing, right branching or left branching. But the branching is according to this schema anyway, in this theory. It doesn't tell you we should do this or we should do that. That's a separate problem, whether it's right or left branch. Good question, but I think that's the situation.
Let's take one more question. Okay, thank you very much.
Thank you.